Okay, so if you remember, we talked about the intersection of two sets. Of course, we talked about the union of two sets and then the intersection of two sets, and we solved some examples related to those concepts. Now, today, we want to talk about the last operation between two sets, which is covered in the book, and that's the subtraction of two sets, the difference of two sets, yes? So let me start with the definition. So let me be consistent. Yeah. So difference of two sets. Yes. So this is my definition. Let A and B be sets. The difference A minus B is defined as follows. Okay, we say that A minus B is equal to the set of all those elements in the universal set such that that x belongs to the first set but does not belong to the second set. Okay, so the difference of two sets is the set of all elements in the universal set such that those elements belong to the set coming first, but they don't belong to the set that coming after that. Okay, so that is the definition of the subtraction of two sets. Of course, I don't know, in set theory books, and I think even in your book, instead of having this usual negative sign, they have denoted by this symbol. I think so in your book. So, but if you see this one, that's also the same thing that I have defined here. So let me write this as a remark. Sometimes A minus B is denoted by B. Okay, so but I usually use this difference, the normal subtraction. Okay. Okay, so let me just draw a Venn diagram to motivate what is this one. So in the most general case, if I want to show where is A minus B, so assume that this is my universal set, and then I have a set A here, yes, and I have another set B. Okay, but then when I say that A minus B, I mean those elements which are in the universal set, they are in the first set, but they do not belong to the second set. So it is clear where they are, yes? So those parts which are in A but not in B. So this part that you see that I am now coloring is actually A minus B. These are all elements which are in A, but they are not in B, yes? So this, if I want to show it here, so this part is A minus B. Yes, so this is A minus B. Of course, if I have, for example, this situation, what will happen for A minus B? Assume that I have this, and this is my set A, for example, and this is my set B. If this is the case, where do you think would be A minus B?
Just A.
Yeah, exactly. The A itself is A minus B. So in this case, I am interested in elements which are in A but not in B. Of course, in this picture, none of the elements from A belongs to B. So it means that A minus B is exactly A itself. So here, this is just actually A minus B. Or I don't know, for example, if I consider this situation, what will happen? Assume that I have this set A, and then another set that I have is completely inside this, for example, this one. And then what is A minus B? Here in this picture, what is that? All those elements which are in A but not in B.
It's like a donut.
Yeah, it's like a donut, yes, exactly. So this becomes this part. So this is A minus B. And of course, let me just throw one more. If I have this situation, might be you are able to guess yourself now, that if this is the other way around. So for example, I have this situation that this is, let me make it smaller. So this is my set A, and this is my set B. Okay, so then what is A minus B in this case?
The empty set.
The empty set. Okay, because I am interested in those points which are in A but not in B. But because A is a subset of B, whatever is inside A, it's automatically inside B. So I cannot find any element with that property which belongs to the first one, not to the second one. So what is left for me is the empty set. So that's the meaning of the difference of two sets using the Venn diagram. Let me start with very simple examples now. So example, so let me write this. Let A be this set A, B, C, D, and B be this set C and D, and C, for example, be this set A and B. Okay, determine A minus B, B minus A minus C, C minus A, B minus C, and C minus B. Okay, they are very, very simple, but let us do it quickly. So we want to determine these sets. Okay, so when you say that I want to determine A minus B, so this is A, B, C, D. Let me write the first one patiently, minus C and D. So you open a curly bracket and then you close it. And then what you are supposed to put here is that you consider elements which are in the first one but not in the second one. A is in the first one, it is not in the second one, so you write it in the answer. And then you go to the next one. B is in the first one but not in the second one, so you write it here. But then C is in the first one and the second one, so you don't write it down. D is the same, it's in the first one and the second one, so you don't write it down. So in principle, if you want to have a recipe for that, what you need to do, you just eliminate the elements on the second set which are in the first set. and then what is left for you is the difference. Yes? But now if I want to write b minus a, then what will happen? So what is b minus a? It is c and d minus a, b, and c and d. Yes? So what is the answer? You are interested in those elements which are in the first one but not in the second one. But if you choose this one, it is in the first one, it is also in the second one. So I cannot choose this. If I take this one, it is in the first one, not in the second one. So what is left for me? Be careful, you are not going to look at here. What you want to choose are the elements from the first set, which of course are not in the second set. So what is left for me? Actually nothing. I am interested in those elements from the first set that does not belong to the second set. There are no elements with this property. So this is the empty set, and then I prefer to write just the empty set. Okay, I paused the video for 2 minutes. I want you to do the other parts yourself, okay? Okay, so I don't think it is hard at all, yes? So if you want to do a minus c, I am interested in those elements which are in the first one but not in the second one, so it is clear that I need to omit them, and then I have c and d, yes? So it is c and d. The next one, for the same reason that I talked before, is the empty set. Okay, so what is your opinion about this one? What is b minus c?
It's B.
It's b itself, because it is what you are interested in, those elements which are in the first set but not in the second one, so they are c and d. But c and d is the name of b, so you see it is not like numbers. You need to it is not correct to draw the analogy between this subtraction and the number subtraction. So here you see that I am taking something out from this set, but what is left is the set itself. And for the same reason, and this becomes the set A and B, which is the set C. So this is very simple. But now if I ask you one question, what is the, in general, what is the relation between A and A minus B and A? What is a relation between these two? Of course, for example, you see this in this Venn diagram, A minus B is exactly equal to A. But of course, here in this picture, you see that this is not exactly equal to A. What is the general relation between A and A minus B and A, which is always true?
A minus
Equality
B
is not.
oh,
Pardon?
A minus B is a subset of A.
Yes, it is exactly. This is good to know that A minus B is a subset of A, because actually it is inherited in the definition of A minus B. You say that A minus B are those elements which are in A but not in B. So it means that definitely the elements that you choose here are inside A. So A minus B in general is a subset of A, but we cannot say more than that, yes, unless we have more information about this. So let me write this as a remark. For any sets A and B, A minus B is a subset of A, and of course, if you want to, B minus A, for the same reason, is a subset of B. Okay, so that's also good to know. Now, there is a very important theorem that relates a subtraction to intersection. Yes? And this theorem is here. So theorem for any sets A and B, we have this relation. A minus B is equal to A, you change the difference to intersection. You change the subtraction to intersection and then complement the second set. So A minus B is equal to A intersection B complement. So that's a very important formula because the number of relations that we have for subtraction is limited, but you remember we had a theorem, 9 parts for properties of intersection. So this is a very good theorem. We change subtraction to intersection and we use all the utility that we learned there for intersection to say something about subtraction. Okay? First of all, let us prove this. Of course, if I go back to this picture, might be it is easy for you to realize it from Venn diagram. So here, A minus B is this orange part, yes? But what is A intersection B complement? B complement means whatever is outside B, yes? Whatever is outside B, I am just showing it for you. So this is whatever outside B. Yes, this is what is outside B. B complement. This part is B complement. Now tell me, if I intersect whatever is outside B, this in the red parts, and the A itself, what is left? You see, A is here. Yes, and these red parts that I hatched vertically is B complement. So if I ask you which parts are hatched twice, so you see that is exactly the orange part. So hopefully this diagram will convince you about the validity of that theorem. But of course, this is not a rigorous mathematical proof. If I want to show this is true, I need to do it systematically. Okay, so I would say proof. Okay, so what is the standard way of showing two sets are equal? I have something which is a set on the left-hand side. I have a set on the right-hand side. I want to show that these two sets are equal. So I need to take a typical element from the left-hand side and show that this is in the right-hand side and the other way around. So I would say that let X belongs to A minus B. We show that X belongs to the right-hand side and the other way around. Okay, but this is very simple. When you say that X belongs to A minus B, what can I conclude from this statement based on the definition? When you say that X belongs to a difference A minus B, I can immediately conclude based on the definition that this X belongs to the first set and this X does not belong to the second set. This is the meaning of X belonging to A minus B. Okay, but now you know how to translate this part. So I can conclude that, of course, X belongs to A. When I know that X does not belong to the set itself, I am certain about that X belongs to the complement of that set, yes? So it belongs to the complement. Now you are telling me that I have an element which simultaneously belongs to this set and that set. Okay, then this means that definitely X belongs to the intersection of these two sets, yes? And then we are done for the first part. If you have any questions, please interrupt me. And of course, this is not enough because we have just shown that whatever is on the left-hand side, it is also in the right-hand side, but we want to show the equality, so it should go the other way around as well. Okay, so here, can I go from here to here? The answer is yes. If you tell me that X belongs to the intersection of two sets, then I can conclude that X belongs to both of them simultaneously. But can I go one step back? Yes, because when you say that X belongs to A, I can just repeat it. That's the same story. But X belongs to B complement means that X does not belong to the set itself. And then this is exactly the definition of this difference of two sets. You are telling me that X belongs to A, and then you are telling me that X does not belong to B. So I conclude that X belongs to A minus B, and then I am done. So that's a very nice relation that you have. A minus B is equal to A intersection B complement. Okay, so let me just write something here for you. So here, if I ask you what is A minus B, you can say that I can write it I repeat the first one, I change the difference sign to intersection, I complement the second set. Yes? For example, if I ask you what is B minus A, if you want to, you can write the first one, you change it to intersection, and then you write A complement. So there is no ambiguity going from difference to intersection, from subtraction to intersection is always unique. But going from intersection to the difference to the subtraction, you can do it in two ways. Yes, for example, let me read it. What does it mean? It means that if I want to go from here to here, I choose to put one of them, I change the intersection to the difference, but I complement my second set and put it here. Okay, but there is no first set and second set when it comes to intersection, because you know that A intersection B complement and B complement intersection A, they are exactly the same. Here, it makes sense which one is coming first, which one is coming the second one, because A minus B and B minus A are not in general equal, yes? But when it comes to intersection, I cannot say which one is first, which one is second, because actually they are the same. So that is up to you. How do you want to interpret that? So if you, for example, what I'm trying to say is that when I say A minus B, you can write it in two different ways in terms of subtraction. You can assume that this is the first one, so you write it as the first one, and then you change intersection to subtraction, and then you complement your second set, so it becomes B complement. Or if you want to, you can interpret this as B intersection A because they are the same. Now you write your first one, change the intersection to subtraction, and you complete that, make the complement of the second one. So whatever you are writing is completely correct here. So let me just repeat. If you want to go from a difference to intersection, you can just do it in one unique way, because when you write A minus B, it exactly means that A is the first one, B is the second one. The reason is that A minus B is not equal to B minus A. Okay? But when I write A intersection B, even though I have written A first, but I cannot mention that A is exactly the first one, because there is no difference between A intersection B and B intersection A. Then if you want to go from intersection to difference, then you can just do it in two ways. As of course, it depends to the problem, which one is more suitable for that problem. I can interpret it as in this way, that this is the first one. So I write the first one, I change intersection to subtraction, then I complement the second. But if I, in my head, if I interpret this in this form, because they are the same, then this is the first one. So I write the first one, and then I write the difference, and they make the complement of the second one. So all of these things that you see here are exactly the same, but of course it is clear that these two are not the same. Any questions? Okay. Let me give a simple example. Simplify. Let me make it short. Simplify. Of course, some of them are very trivial, but let us just do them patiently. Okay, so number one, I have a set A, I subtract the same set from itself. So it is clear what is left.
The empty set.
The empty set. But let us see why. I always use this theorem, okay? So here, if I want to use this theorem, I write the first one, I change the difference to intersection, and then I complement the second one. So it means that I reduced the answer to this question to a property of intersection of sets that I already studied, yes? So, but you know that what is A intersection A complement? Everyone knows that the answer is the empty set. So what you said is completely right. Let me do another one. So here, what is A minus A complement? Okay, so what is your guess before calculation? A minus A complement. What is your expectation?
It's A.
It's A, yes, because A minus A complement means all elements from the first set which are not in the second set. But of course, the second set is the complement of the first one. So whatever is inside A automatically is not in the second set. So you will write all of them. But if you want to use this theorem, how should I do that? I will write the first one. I will change the difference to intersection. Then I will complement the second set. But then you know another property of complement. So what is that? A complement is equal to A itself. But again, you have another property for intersection. Any set intersection with itself is equal to itself. So your guess was completely right. Okay, so I don't know, what do you think about this situation now? If I have A complement first minus A. So let me write some of them. You can also think about them yourself. Yeah, you can start writing them. I think I can fit it here. Okay, so these are simple, yes? So did you get the answer to the first one?
Yes.
Yes, what's the answer?
A complement.
It's A complement, yes? So it is A, the first one I write, I change the difference to intersection and the second one to complement. So I will complement the second one. But now I have A complement intersection with A complement. Any set intersection with itself is equal to itself, including this complement set. So the answer is A complement. Okay, so what is for A minus U? A minus U universal set. It means that everything in A, which is not in the universal set, but this is not going to happen because whatever is inside A is automatically inside the universal set. So your guess is that you will get empty, but the calculation also shows that this is empty. Why? Because I write the first one, I change the difference to intersection, then I complement the second set. But you know that the complement of the universal set is the empty set, and we learned that the intersection of any set with the empty set is the empty set. And then if I go to the next one, so what's the answer?
A complement.
It's A complement, yes? So it is clear. It tells you that whatever is inside the universal set but not in the set itself, that is exactly the definition of the A complement. But the calculation also shows that. So I will write the first one, I will change the difference to intersection, I will complement it. But we learned that intersection of any set with the universal set is the set itself. So it becomes A complement. Now let me do these things quickly. So this becomes A intersection empty set complement, but we know that empty set complement is the universal set, and intersection of any set with the universal set is the set itself. And then, so in numbers, if I have 0 from a number, it becomes negative of that number, but this is not exactly the same. So these are sets. So what's happening here? It becomes this first set intersection with the complement set. So, but any set intersection with the empty set is the empty set. Okay. Let me give you another example. Let me write simplify. I want to wait for you a little bit. Simplify. So number 1, A minus A minus B. Number 2, A minus B minus A. Okay, I paused the video. I want to wait for you 3 or 4 minutes. I think is enough. Okay, so let us do it. Okay. First of all, I just want to mention again, so don't think that you can multiply the negative sign inside or whatever. So might be this is the reason that people use this symbol to show that they are not the same. This is not algebra, because in algebra I can multiply the negative sign in, it becomes minus A plus B, and I can say that A and B and A are gone, so the answer is B. So this is not the name, this is not the same as subtraction. Might be some properties are the same, but usually they are not the same. Okay, so that's the first thing. And I think if you have done this right, what is your answer you got for this? Did you get the answer?
Is it A intersection B?
Exactly. So that is A intersection B. Okay. So, and of course, if I go back to the Venn diagram, so remember this combination, you want to determine A minus B. So if I go here, you can easily convince yourself by the Venn diagram. So Venn diagram is a very important tool in our hand if I just want to have an educated guess for the result, okay, independent of the rigorous way of proving it. So here, this part is A minus B. Now I want to determine A minus B. It means that I want to color all those parts which are in A, but they are not in this orange part. So you see, it becomes this part. But there is another name for this part, and that is the intersection of these two sets. So you see that Venn diagram immediately shows the answer to us, okay? But if I want to do it rigorously, so what should I do? I would say, number 1, so what we should do, there are 2 subtractions that I need to take care of. So let me just start with this one in the pair of brackets because it prioritized this subtraction over that subtraction. So I will write A minus, this is the copy paste part, and then instead of A intersection B, sorry, A minus B, I write A intersection B complement. Yes? But now there is another difference left. So what I need to write, I need to write the first one. I change the difference to intersection, but I have to make the second set, I have to consider the complement of the second set. But this expression as a whole is my second set. So this means that I need to consider this complement. Okay. Okay, Khulud, yourself, can you tell me how should I continue? This is the way that you did it or not?
It was Sarah who answered, but
Okay, sorry.
yeah, but you just
So Sarah, can you answer yourself now?
oh yeah. Well, I got then at the end A intersection B, and then A intersection A is A, so it's A intersection B.
No, so there is some missing point here. Can anyone correct that?
Can I
so you
answer?
Pardon?
I said, can I correct?
Yes, you can.
We take A complement union B.
Yes. Why?
Because when we complement,
Yeah, that's called De Morgan. Yes, do you
yes.
remember? So, yeah, exactly. That's the. So let me thank you very much. Now it's correct. So you see, that was a delicate actually mistake. So you need to be careful about that. So here, if I have A intersection B and I want to find the complement according to De Morgan laws, I can complement the first one. I can complement the second one. Do you remember De Morgan? We talked about these laws. Okay. So then I have to change. Oh, sorry. I have to change the. I can write this, but I have to change the intersection to union and the other way around. So that is the main point here. So you can write A intersection, you open a pair of brackets, you write the complement of the first one. If I want to write all the details, let me write all the details. And then I need to complement this. So this is De Morgan, yes. And then we know another property that complement is the same set. So this becomes A intersection A complement union B. Okay, then what? Can anyone continue? So you see that the calculation, if you want to do it rigorously, it is a little bit lengthy, even though it was very easy to guess from the Venn diagram what the answer is.
Yeah, I forgot you had to complement the whole bracket thing.
Okay. But anyway, now can you tell me how should I continue?
We use the distributive law.
Exactly. Thank you very much. Because one of them is intersection, one of them is union. Why this is not absorption law? Because none of them is repeated. If one of them was repeated, so of course the answer was the repeated set, but none of them is repeated, so I use the distribution law. So this becomes A intersection A complement union A intersection B, yes? So what happens now? We know what is the answer to this part is the empty set. And then I have union, and then I have A intersection B. But I know that the union of any set with the empty set is the set itself. So what you guessed is correct, but that is a mathematical way of showing it. So you see, I am using a lot of rules here. So one theorem that we learned today, and then the Morgan laws, the complement of a complement is equal to itself, distributive law, intersection of any set with itself is the empty set, union of any set with the empty set is the set itself. So all these rules that we learned before are somehow being used. Not all of them, some of them. Is that clear? Okay.
Yes.
Okay, now let us go back to Venn diagram to have to try to guess an answer for this, because the Venn diagram is much more quicker, okay, intuitively. So here I want to have A minus B minus A. In algebra, we can write A minus B minus A. I can write A minus B plus A, then I can write 2A minus B. Of course, this is not the, this is not the answer, of course, here, but let us try to go back to this Venn diagram to see that if we can guess. Okay, using this one, first of all, where is B minus A? B minus A is this part, everything in B which is not in A. So this part that you see right here is B minus A. But what I am supposed to do, I am supposed to write A minus this. It means that whatever is inside the A, but they are not inside this red part. Can you tell me what the answer is? Everything inside the set A, but not in the red part.
Just A.
Just A, yes. Everything in A, which is not in the red part. Everything in A, which is not in the red part, but everything in A is automatically not in the red part. So we guessed that the answer should be A. Okay. Now let us go back and try to calculate this. Okay. Of course, calculate is not a good word here, to determine this set. So, okay, but let us do it again as before. Here I have two subtractions, but this pair of brackets prioritize the second one. So I will write A minus, then it becomes B intersection A complement. I think you have enough experience now, so I will change this one now to intersection, but the price that I have to pay is to change this to its complement. And then again, De Morgan law comes to my help. So this becomes B complement union A complement complement. Okay, now this is the tricky part. So A intersection B complement union A. Can you tell me what's the answer? Or how should I get to the answer?
The absorption law.
This is the absorption law. So why? Because it's exactly similar to the distributive law, but one of these sets is repeated. If that's the case, if you start doing it using distributive law, if you remember, it becomes a circular argument. It goes back to something which is true. If you do it once more, it will go back to the same expression. So it is not helpful. So here, the absorption law immediately comes to my help, and I will get the answer to be A. So let me write here. Okay, so what we get here is exactly according to what we were able to guess using the Venn diagram. So that is the important point about the Venn diagrams. They are very intuitive tool in our hand when we are dealing with sets. Okay, okay. Now I want to give you another example to wait for you a little bit and then start the last bit of the set theory, and then we finalize everything for the set theory. Okay. So here, example. For any sets A and B, show that number one, A union B minus B is equal to A minus B. Number two, B minus A union A intersection B is equal to B. Okay, so I will wait for you 5 minutes, I think is enough. Okay, so I think it's not that hard. So here, first of all, this is an identity. I want to show the equality is true. So I would start from one side usually and do some algebra on the sets and then try to reach to the other side. And usually it is better to from that side, which is more involved. Yes. So for example, if I want to do this one, I prefer to start from the left-hand side. Okay, now can anyone tell me how should I start? What is the first step?
You do A union B intersection B complement.
Yes, exactly. That's the first step. Because usually the number of properties for subtraction is very limited. So it's better to get rid of that as soon as possible so that we can have more options available. Okay, so that's very good. Okay, can you yourself continue what to do after that? Anyone else?
Should we use distributive law?
Exactly. That's distributive law, but so don't get confused. First of all, is it distributive law or not? I have this combination. One of them is union, the other one is intersection. Is any set exactly repeated? No. So this should be a distribution law. Of course, always I have distribute from left, but there is no problem because if you are not comfortable with this, you can change it in your mind, even though this is not mandatory. This part is not mandatory, but I just write it in this way because there is no difference between this one and the intersection, this one, or the other way around. Now might be this is easier for you to see it, but if you start distributing from the right hand side, that's also okay. But anyway, so I distribute it inside, so it becomes B complement intersection with A, and then I have a union B complement intersection, sorry, B complement intersection with B. But then hopefully this is clear that B complement intersection B is the empty set. So this becomes B complement intersection with A, and then union with the empty set. But any set union with the empty set is this one. But then we need to have an eye on the right-hand side. On the right-hand side, I want to reach to A minus B, but then it is clear. So let me change the order once more. There is no difference between these two expressions, but this is exactly the theorem, yes? This is exactly A minus B, and that is equal to the right-hand side. So I was able to show that the left-hand side is always equal to the right-hand side. So it doesn't matter what are the elements of these sets. This combination is always equal to the difference of A minus B. Okay, so let me just do this one also. Anyone else? What is the first step to do? First of all, I think it is clear for everyone. It is better to start from the left-hand side, which is because it's more involved. But what is the first step that I need to take here? Anyone?
You can rewrite the B minus A to B intersection A complement.
Exactly. And then what is the next step?
You can split and create two, what's it called? Like, basically you do B union A intersection B intersection A complement union A.
No, you are making it. I understand what you are saying. You are saying that you want to distribute this inside, yes?
Yeah, but I don't know if that's
But
allowed.
No, but I think there is a much simpler way.
Okay.
Now, anyone else?
Oh yeah, maybe the. Oh, sorry.
Oh, no. You can continue.
Maybe the absorption law will work because it's the same.
No. Absorption law doesn't work here because nothing is exactly repeated. Yes. Yes, Khulud?
It's B. It's repeated.
Okay, no, B is repeated, but you. So
yeah, I know. It's the distributive law.
Yes, it is the distribution law, but there is a name for that because you see, when I say that A intersection B union C, I distributed from the left-hand side to the right-hand side. What I am writing is called distribution. Yes, but I think now you see that this is similar to this one. I want to go backward. The backward is factoring out, yes? So it means that I can find something in common in these two pair of brackets and pull it out. I don't know, can we call it factor out? Because in numbers, when we write a number as a product, each one of those is called a factor. So this is meaningful for the numbers. But yeah, some analogy, if I want to draw an analogy, I can say that, okay, I can pull something out, but I want you to understand that this is not the absorption law. If it was B, only B, union A intersection B, this is the absorption law, and I can answer B. But this is the whole package. You cannot separate it from here and say that this part with this part is the absorption law. No, the absorption law should be exactly of this form. Okay, so what I want to write, let me write B intersection A complement as it is. Of course, this is not mandatory, but let me write it exactly. Instead of A intersection B, I can write B intersection A. Okay, and then now you see that there is here B intersection, I can pull it out. So it becomes B intersection, and what is left from the first one is A complement union. What is left from the second one is again A. But then it is easy now. B intersection A complement union A is the universal set, and any set intersection with the universal set is the set itself, and that is exactly equal to the right-hand side. Yeah, is that clear?
Yes.
Okay, now let me just go to the last part of the lesson, and that is regarding the cardinality of the sets again, the union, and so the union of the, so that's my point. Let me write the theorem first for you. Theorem. Let A and B be finite sets. Then, do you remember this symbol, similar to absolute value, is also used for the cardinality. So the cardinality of A union B. So one common mistake is that the cardinality of the union is equal to the cardinality. Cardinality is a big word. It's just a fancy word for just the number of elements. Yes, when I say the cardinality of a set, I mean the number of elements in my set. Do you think this is in general a true statement? Might be this sometimes intuitively seems to be right. The number of elements in the union is equal to the number of elements inside A plus the number of elements inside B. Do you agree with this statement in general?
No, not at all.
Yeah, it is clear that this is not correct. Yes, for example, let me just write something and I will clean this. So this, if I have this A, this, and if I have B, this, if I ask you what is the cardinality of A, you say 2. If I ask you what is the cardinality of B, there are 2 elements. This is again 2. If I add them, the cardinality of A plus the cardinality of B is 4. But if I ask you what is the cardinality of the union, you first union them. Because in the union you do not repeat elements, the union is 1, 2, 3. And if I ask you what is the cardinality of the union, the answer is not 4, the answer is 3. And then you see that they are not the same.
Mr. Babak, there is a way to fix that.
Yeah, exactly. There is a way to fix that, and that is the content of this theorem. But first of all, I want you to understand that this somehow intuitive idea is not correct. And the reason that this is not correct, because when we want to do the union, if there is an element which is repeated, we do not repeat it. Okay, so that's the reason that this formula is not correct. Okay, but now can you say, Alex, how do you want to fix the correct one?
Just do minus the cardinality of A intersection B.
Yes, so what is left? So you see the reason that this was not correct is because 2 was in the intersection, which was counted only once here, but it is once calculated here, once counted here, so it is counted twice here if I don't care about this. So this is the formula that you need to know. If I have 2 finite sets, the cardinality of the union of these 2 sets is the cardinality of the first one plus the cardinality of the second one minus the cardinality of the intersection of these two sets. Only if the sets are disjoint, then of course that is correct. Because if the sets are disjoint, it means the intersection is the empty set and the cardinality of the empty set is 0. So this is gone, and then I will get this one. So this happens if and only if the intersection of two sets is equal to the empty set. Okay, and then so here, if I want to give a proof for this, so one way of proving this is something like this. I would say that let X be an element in the universal set. Okay, so what are the possibilities for this X? So if I want to draw a diagram for you here to make it simpler to understand, so this is just intuitive. So my reasoning will not rely on this diagram, but it makes it easier for you to understand. So assume that this is my A and this is my B. Okay. So when I say that I have an element in the universal set, this X might be here, might be here, might be here, or might be here. There are 4 regions, different regions with different borders here. And these are the 4 possibilities, yes? Okay, so if X, I want to talk about this orally because it takes a long time if I want to write it, okay? And this is very simple. If X is here, how many times I counted here? Can you tell me? Is it counted in the union?
No.
No. So on the left-hand side, if X is there, it is counted 0 times on the left-hand side. But how many times it is counted on the right-hand side? Here, it is not counted, so 0 times. Here, it is not counted because it is not there. Here, it is not counted, so it is 0. So if I calculate, this number is 0. So for this situation, the left-hand side matches with the right-hand side. But then, of course, it might happen that my X is somewhere here. If my X is here, how many times it is counted on the left-hand side? Once, because it is in my union. So 1 time it is counted on the left-hand side. Is it counted here? Yes, 1 times. Is it counted here? No, 0 times. Is it counted here? No, 0 times. If you add and subtract these numbers, you get again 1, and these 2 numbers again match. And for the same reason for this one, but let me consider this one. Assume that my X is here. How many times this X is counted here? It is counted here how many times? 1 times. Yeah, 1 time. And then how many times it is counted here? 1 time. How many times it is counted here? Again, 1 time. But how many times it is counted here? Again, 1 time. So 1 plus 1 minus 1 is exactly 1. Again, these 2 numbers match. Okay, so take this oral part as the written proof of this. I don't want to spend some time on it to write it rigorously. But that is the idea behind that. And of course, from this picture and intuitive, it's completely clear. Another way is that, okay, when I say A, I am just considering all these parts. And when I say B, I am considering all these parts. But when I want to talk about the union, I need to consider all the parts inside A and B. But you see that this part is counted twice because it has been hatched both horizontally and vertically. But my goal is to count it once. So I take one of them that I counted extra. And that's the formula. So anyway, this is a formula that you need to know. Okay, and then there is also another one. Let me bring an example here. So in practice, there are some examples that you need to know how to work with. So let me make it a little bit bigger here for you to save some time. instead of writing. So let me write this, talk about this example. So there are 35 students in a class, 15 students play football, and 23 students play basketball. If 5 students play neither football nor basketball, how many play both? Okay, so something like this. Even though you can usually use the formulas, but I always prefer, and I think it's also good for you, I recommend you to draw a Venn diagram all the time. So then you don't need to memorize any formulas or anything. So here, what I can write is this. If I want to solve such a problem, I will do like this. I will try to draw a Venn diagram for myself. Yes. And then the sports are football and basketball. So for example, I will draw something here and call it football, for example, F. And then I draw another one, something like this, and I will call it B for basketball. Yes. And then I read this. There are 35 students in a class. So instead of this universal set, so this is my class, yes, which plays the role of the universal set here. So we know that what is inside this big rectangle are 35 elements. 15 students play football. So if I want to solve this problem, I recommend you to do this one yourself exactly in this way. So I will put X here. It means that I assume that the number of elements here, this means that the students which are playing both football and basketball is X, which is exactly the thing that I want to answer. How many play both? Yes, I don't know. But I know that 15 students play football. Yes, so 15 students should be in this green part. But already I took X of it here. So what is left for me is 15 minus X, which I write here. And then if I continue to read, 23 students play basketball. So in this blue part, there should be 23, but X of them I have already put here. So what is left for me is 23 minus X. And then 5 students play neither football nor basketball. So what I know is that 5 students are outside, both of them. Okay, so how should I solve the problem? It's very clear. There are 35 students. 5 of them doesn't play anything at all. So what is left for me is 30 students. And this 30 students is equal to these parts. The number of elements here, plus the number of elements here, plus the number of elements here. I need to add them, yes? So this becomes 15 minus X plus 23 minus X. So if I simplify this, it becomes 30 on the right-hand side. 15 and 23 is 38. Minus X and X are gone, so this becomes this. And I simply solve this equation by moving X to the right and this number to the left. So X becomes how much is 8. So the answer is that 8 students play both. The reason that I am encouraging you to draw a Venn diagram, because the problems could be harder. This can be involved with three actually sets or more. Okay, so even there is no more in the book, so don't worry. You can have at most 3 sets. But here, let me also write the remark before leaving this, and that remark was as before. So as I told you, the cardinality of A union B is equal to cardinality of A plus cardinality of B if and only if A intersection B is empty set, is the empty set. Okay, of course, A and B should be finite sets. Okay, so this I want to write it as a theorem because this is a problem in the book. I think it's a level 3 problem. So let me write it as a theorem. And the question is that how can I write a formula for 3 sets instead of 2 sets? So I am interested in the union, in the cardinality of the union of these 3 sets. Yes? So let me write it down here for you. So let A, B, and C be finite sets. So the union, so let me start from here. The union of the cardinality of the union of these 3 sets is equal to, the formula is a little bit more complicated. It is the cardinality of the first one plus the cardinality of the second one plus the cardinality of the third one, but minus the cardinality of mutual intersections, means A, B, minus the intersection A and C, minus intersection B and C, and then finally plus the cardinality of the intersection of all of them. Okay, so this is the a problem in the book. So this is the formula. So for the formula for 2 sets is more or less easily understandable. But when we go to more sets, for 3, the formula becomes a little bit more complicated. Using this pattern, you can guess what would happen for more than 3 sets, but that is not part of your lesson. Okay. Here, I want to spend time on proving this, and then I will write just one example and leave it for the next session. Okay, so let us prove this here. I think the starting part shouldn't be hard because this, you have enough experience by doing this. You see, here I have 3 sets. I want to find the cardinality of the union of 3 sets, but I know the cardinality of the union of 2 sets. Whenever this happens, I can view this union as the union of 2 sets by putting a pair of brackets around 2 of them. Yes, so this is equal to the cardinality of A union B union C. Yes, this is correct because the union has the is associative. So when it is associative, it means that it doesn't matter if you put a pair of brackets around these 2 or if you put a pair of brackets around these 2, the answers are the same. So because union is associative, I can just do it like this. But now if I ask you how many sets are involved, you can call this capital B, and then you have A union capital B, and then you want to know the cardinality. So, but we know the formula for 2 sets, yes? It becomes the let me make it smaller. So it becomes the cardinality of the first one plus the cardinality of the second one minus the cardinality of the intersection of these 2. So this becomes the cardinality of the first one plus the cardinality of the second one minus the cardinality of the intersection of the first one with the second one. Yes? But now I can continue. The cardinality of A is just the same. But again, here I have 2 sets. I am interested in the cardinality of the union of them. So it becomes the cardinality of the first one plus the cardinality of the second one minus the cardinality of the intersection of these 2. But the problem here is that this is intersection, not union. But then I can use distribution law, yes? So what can I write? I can write minus. Inside this, I can do this distribution. A intersection with B, union A intersection with C, yes? Now again, the problem is solved because now this is one set, this is the second set, and then I have the union between these 2. So again, I can use this theorem for two sets. Yes. So let us make it clear. So let me just write it. I just copy and paste the first parts. But now I can write, I open a pair of brackets because of this minus sign. This is two sets. The cardinality of the union of two sets is the cardinality of the first one plus the cardinality of the second one minus the cardinality of A intersection B intersection A intersection C. Yes, hopefully I can fit it here. But let me ask you, can I simplify this a little bit more? You see here, all the operations are intersection. So I can move them around in any order that I want, but I have A repeated, yes? So what I do, I can write it as intersection A, intersection B, intersection C. There is no difference between this one and this one because all of them are intersection. But then A intersection A has a better name, it is A. So that expression is nothing except A intersection B intersection C. And then I am done. So this becomes, so let me change my color. So this becomes intersection of A plus intersection of B plus intersection of, sorry, plus the cardinality of C minus cardinality of this intersection. Then I will apply this minus sign here. It becomes negative, but the last one, which is negative, becomes positive. So this becomes minus, minus, and then plus. Yes, so as I told you, there is no difference between this and this. And that is the formula exactly that we wanted to show here. Okay, I just copy and paste an example. If you want to, you can work on it. Next session, I will complete everything, and then maybe I will give you some extra time to practice on yourself before going to the next lesson. So what I want to do is just this one. And then if you have to leave, you can leave, but then I will upload this on YouTube, and then you will have access to this. So that is also a good problem, but this problem involves three sets. But again, I recommend you not try to use this formula. It is a little bit complicated. It's better to draw a Venn diagram for yourself and try to analyze the problem before solving it. Okay, any questions? Okay, so I stop this video here.